Hello everyone, let's learn about semaphores in this lecture. So semaphore provides software solution to the critical section problem, or you might say that semaphore is a mechanism to implement mutual exclusion. That is, whenever a thread or a process proceeds to update a shared variable, all other threads or processes are excluded from doing it simultaneously. So it contains a protected variable that can be accessed and altered by only one of the operations, a P operation or a wait operation, and a V operation or a signal operation. So let's try to understand that with using an example. So you've gone to a restaurant and you're waiting for your food. You've already placed the order for the food, now you're waiting for that. Next, the waiter arrives, places the food in your table, and he goes away. So, while you're having your food, the waiter is waiting for delivering you the bill. Now, he can't deliver you the bill, so long and so forth. You are having your food. So, after you've had your food, you reach out to the waiter saying, "Bill, please," and now the waiter can deliver you the bill. So, what we have seen here is, so long and so forth, the waiter does not place your food on your table, you can't have it, and so long and so forth, you don't signal that okay, now I'm ready to pay the bill. The waiter of course can't deliver you the bill. That is in normal circumstance. So let's see how the code works in case of semaphores. Now this wait code is like, um, the S indicates that S is a semaphore variable. In our case, let that semaphore variable be food. Now, first, when you're trying to have your food, you will need to check that if there is indeed any food in your table. So that is done using this while loop. So while the value of S is less than equals to 0. Now less than equals to 0 in our example means um, the food is 0, which means there is no food in the table. So we will need to keep waiting. Now the waiter comes in with the food and the variable s is incremented. S becomes s plus 1. In our case, there was no food which was indicated as f equals to 0. Now this value of f changes to 1, and now you can decrement, that is, you come out of this while loop or you stop waiting and you can have your food now, which is indicated as s minus minus. So these semaphores are mostly used for mutual exclusion, where whenever a process wishes to enter the critical section, it will need to execute the wait operation to find out if there are any other process already in the critical section. And whenever a process needs to come out of the critical section, it will need to execute the signal operation or the V operation, and then only it can come out. So what happens here is, in this particular case, as we can see, we have a critical section which is empty as of now, and we have a semaphore variable s whose value is 1. Now let a process or a thread come in. Let a process comes in. Let that process or thread be indicated as T1, and that process needs to enter into the critical section. So it executes the P operation on the semaphore S. Now what the P operation does is, it first checks if the value of the semaphore or S in this case be greater than 0. Now in our case, the value of S is 1. So this evaluates to true and this statement is executed. That is, S is changed to S equals to S minus 1. So what happens now is, the value of S is changed to 0 and the process or the thread T1 enters into the critical section. Next, say another process or a thread comes in with a and it wishes to enter into the critical section. So it will also need to execute the operation PS. Now in this case, this if condition, it checks that if there are any other process in the critical section already. In our case, The S value has been changed to 0, and of course we have a process T1 which is already in the critical section. So this if condition fails. Now it has to execute the else part, which says that the calling thread is placed in the semaphore's queue of waiting threads. Now what happens is a waiting queue, say wait queue S, associated with semaphore S is created, and this process T2 is added to this queue, and T2 is blocked. That is, T2 cannot further execute any line of code, and T2 is waiting to enter into the critical section. Now say process T3 arrives, T4 arrives, all will come in, and all the processes will be executing this P operation, and since there is a T1 inside the critical section, this condition will always fail, and the else part will keep executing, and they will be placed subsequently in the wait queue S. And say up to Tn, the processes are waiting in the wait queue. Now after some point of time, T1 has finished executing in the critical section, and T1 executes the V operation since it needs to come out of the critical section. Now for the V operation, we see that if any threads are waiting on S, resume the next waiting thread in the semaphore's queue. Now what happens is, it is checked that if the wait queue is empty. So if the wait queue is empty, this part will be executed. That is, S value will be changed to 1. But in our case, the wait queue is not empty because we have processes from T2 to Tn waiting in the wait queue. So the if part will be evaluated to true, and the next waiting thread. Now the next waiting thread means the first thread or process which tried to enter into the critical section. In our case, T2 was the first process after T1 arrived. So now T2, so first T1 is made to exit from the critical section, and then T2 is removed from the wait QS, unblocked, and placed inside the critical section. So in this way, the semaphores are used for mutual exclusion. Now one might ask that if a particular thread or a process can wait for more than one semaphore. So the answer will be false, because whenever a thread is made to wait to enter into the critical section, that is, the thread is busy waiting, it cannot execute any line of code. So definitely it can't wait on another semaphore. So that also leads to a problem which is known as a blocking problem. Say in this example, we have two semaphores, M and N, both have been initialized to the value of 1. Now we have two processes A and B which are executing in an interleaved fashion. So first, say the process A, who wishes to enter into the critical section which is associated with semaphore M, it executes this operation wait M. And next, B needs to enter into the critical section associated with N, and B executes wait N. Now both are inside their critical section, respective critical sections. Now while process A is still in the critical section associated with M, process A needs to access the critical section which is associated with N, and it needs to execute wait N. Now the value of M and N is 0, because as soon as process A said wait M, the value of M was changed to 0, and process B said wait N, the value of N was changed to 0. Now since the value of N is 0, process A will be blocked and placed in the waiting queue which is associated with N. Next, say process B is still executing in the critical section. Now process B needs to access the critical section which is associated with variable M. Now it will execute the wait m operation, and since the value of m is 0, process B is also blocked. Now neither of the processes will be able to proceed, and that will lead to a blocking situation, and finally it will be a deadlock state, because in order to uh, order to unblock this process A, this wait n, the value of n should be equals to 1. In order for this value of n to be 1, process B needs to do a signal n, which it cannot do because it's waiting for m, which is again blocked. So both the processes are actually waiting for each other. So this is a deadlock situation. Now, apart from mutual exclusion, semaphores can also be used for process or thread synchronization. Suppose a process or a thread needs to be notified about a particular event, and another thread or a process is capable of detecting that if that event has occurred. The thread who needs to be notified can call a P operation or a wait operation on a semaphore whose value indicates that if that event has occurred. If that event hasn't occurred, it will be blocked till the event has occurred. And when the event occurs, the detecting process or the second process or thread, it executes a signal operation, and then the first process can proceed. So in this case, in our example, say there is a manager who writes the bills, and now she needs a feedback from the waiters that if a particular table um, is almost done having their food, or has asked for the bill. Say you were sitting on table number 8. Now the manager asks the waiter that if is table 8 done yet. So if the waiter, as long as the waiter does not respond to the manager will be blocked. Now, after a while, so the waiter says that yes, then the manager will be unblocked and she can continue with writing the bills. Now, in this case, we can say that if that writing bill be a semaphore with a value b equals to 0, where the manager needs the information that if the table number 8 needs a bill, it is waiting on the semaphore B. And when the waiter signals that yes, you can write the bill, it serves at the signal operation on B, or a V operation on B. Now, in the first case, as we have seen, the manager asks if the table 8 is done yet. So in that case, it checks that the B value is 0. But it might be that before the manager asks, the waiter comes in and he says that okay, table 8 needs a bill. So in that case, the value of B becomes 1, and now when the manager tries to write the bill, it knows that the value of B is already 1, so it can write the bill without getting blocked. Next, another use of a semaphore is counting semaphore. Till now, what we have seen, it's a binary semaphore. That is, the variable semaphore can assume the value of 0 or 1. But in this case, the semaphore which is used for resource allocation, usually the semaphore is initialized to the number of resources. Say we have 3 or 4 printers which are available in the system. So the semaphore in this case is used as a counter, and say we have X number of printers, and we have the semaphore variable associated with printer be indicated as R. So the value of R, or the value of the semaphore, is initialized to the number of available printers, that is X. Next, whenever a process needs to access a printer, it will need to execute the P operation, and the P operation will decrement the value of X by 1. That is, if the printer, if the process gets access to the printer, the number of available printers will be one less than what it was. Similarly, whenever a process releases a resource, or a printer in this case, it will execute the V operation, which will uh, increment the value of X by 1. So there were 3 available printers in the system, and another process X was using the printer, another printer. So once X is done, X will release the printer, and now the available printers in the system becomes 4. So this is how it works. So let's do some examples on example problems on this semaphore. In this question, what we see is there are 3 processes, P1, P2 and P3, which is sharing a semaphore for synchronizing a variable. The initial value of semaphore is 1. Assume that the negative value of semaphore tells us how many processes are waiting in the queue. So processes access a semaphore in the following order. Now let that semaphore variable be S. Now it says, okay, it has the initial value of 1 as per the problem. Now P2 needs to access. Therefore P2 will execute a wait operation, and now the value of semaphore becomes 0. Next, P1 needs to access. P1 will further, it will also execute a wait operation. It will further change the value of semaphore to -1. Then P3 needs to access, so again a wait operation on semaphore, and the value of semaphore now becomes -2. Then P2 exits critical section. That means it will do a signal operation, and now the value of semaphore is increased by 1, and now it becomes -1. Then P1 exits critical section, again a V operation or a signal operation, and the value is again incremented by 1. So in this case, -1 is incremented to 0. So the final value of semaphore will be 0. Let's see another example problem where there are a set of n processes that executes the following code using 2 semaphores A and B, which has been initialized to 1 and 0 respectively. Assume that count is a shared variable which is initialized to 0 and not used in code section P. Now, if every process need to first execute the code section P, then these lines of code, and then code section Q. So as per given in our example problem, this came in GATE to 2020 CSE paper. So the value of A is 1, the value of count is 0, and the value of B is 0. So say the process P1 is done executing in the code section P, and it enters into this section. So it first executes wait A. Wait A will decrement the value of A to 0. Next, it executes count equals to count plus 1. So count value becomes 1. Next, it will check if count value is equals to n. So count value is not equals to n, so this signal B will not be executed. It then jumps to this section where it says that signal A. Signal A indicates that we need to increment the value of A, and A value now becomes 1. Next, it will execute wait B. Now as soon as it executes wait B, since the value of B is 0, P1 will be blocked and it can't move any further. In order for this process P1 to get to this part, the value of B needs to be equals to 1. For value of B needs to be to change the value of B to 1, we need to execute this line of code, that is signal B. Now signal B will be executed only if the value of this if loop evaluates to true. Now in order for the value of this if loop to evaluate to true, the value of the count variable needs to be equals to n. Now how is the counter incremented? Whenever a process enters into this section, the count value is incremented by 1. So when the process Pn finally enters into this section, the value of the count will become n, and then only the signal B will be executed, and that will change the value of B to 1, and then the first process waiting, that was P1, will be unblocked, and P1 will execute signal B, which will again change the value of when it is unblocked. First the value of B will become 0 because this will be executed. Next, what will happen is it will execute the value signal B. So signal B will change the value of B to 1 again, and the other processes can also proceed one after the other, P2 up to Pn. So what it does, it ensures that no process executes code section Q before every process has finished code section P. Indeed, because after the signal B, P1 enters into this code section Q, and then P2, and then every other process. But P1 cannot enter into the code section Q so long and so forth the process Pn has not finished executing in this code section. So this is the right answer. So that was all for today regarding semaphore. There is a link given in the description box to a website that contains some MCQ assignments on semaphore. You can try solving that. If you have liked the video, then please give me a thumbs up and share it with your friends as much as you can. So thank you, and stay